everyone. Welcome to Earth Science. No, I'm just kidding. Just kidding. Don't panic. Here we are in the solar system, and yet we're not really going to talk about Earth science, but we're going to talk about the planetary model of the atom. Now, usually we would walk through history and talk about the different discoveries that led to our modern image of the atom. I want to begin at the end. I want to begin with the correct picture of the atom. Now, this is not quite how we picture an atom today. So in topic 1 of your book, you have this little diagram that's a march through history. It comes right after the section where they talk about the history, early studies, discovering different parts of the atom. But again, I would like us to have an accurate picture and then go back and reflect on how we got to that accurate picture. I am mostly going to be talking about this. Bohr is Niels Bohr. And if you read this, the representation, cannonball, plum pudding, nuclear, planetary, and wave mechanical atomic models. So this is the planetary model. And this is the wave mechanical model. This is the present model of the atom. So why aren't I talking about the present wave mechanical model of the atom? Well, look at it. It's a mess. It just looks like clouds. And the major difference between the planetary model and the modern model is that these electrons out here, and I have added little negative and positive signs, by the way, these electrons that are acting like planets, they are not going in perfect orbits. They're more cloud-shaped orbitals. That is the only difference. But when you start drawing cloud-shaped orbitals, you end up with clouds on clouds on clouds, and you end up with a picture that just looks like a mess. Okay? So this is this, but these perfect circles are cloudy spheres now. Now, how hard is it to draw cloudy spheres on a flat piece of paper? Pretty difficult. Most of the time, I'm going to draw atoms like the planetary model and just have in the back of your head that everything is cloudier. Okay? So, let's start by flying through a planetary model that you hopefully already understand. Our planets. Really, it should be a solar system model, right? The planetary model, it's not like the atom is acting like a planet. It's like the atom is acting like our solar system. So, here we have a car. And I want you to imagine, you could close your eyes if you want. This isn't the best picture of the solar system. Sorry. But I want you to imagine that you're outside of our solar system and you're going to fly in, from the outside in. Maybe the Voyager 1 and 2 satellites that have exited our solar system, maybe for some reason they do a magical U-turn and they start coming back. Okay? So I've set up our planets and the sun, and I think I've done it correctly. We're so used to going from the inside out, right? So Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, rest in peace, Pluto. So Pluto's not a planet anymore. Here we are, we're going to fly in our, we're going to pretend we're spaceman in our little Tesla car. We come in from the outside, and maybe we see Neptune, the blue planet. And maybe as we drive in, oh, there's Uranus. But then look what happens. Do I see Saturn? Do I run into Saturn? In this little car, in this gigantic solar system that's clearly not drawn to scale? No, why don't I see Saturn? Because Saturn is way over here in its orbit. Okay? Any of these planets could be anywhere in their orbit. They could be on the other side of the sun. I should have put some of them on the other side of the sun because chances are, right? So as I come in, I hit this line. I can't see this line. I can't see that Saturn's over here. Okay? I come in closer. I don't see Jupiter. Jupiter's over here. So what have I been doing since Neptune and Uranus? I've been driving through empty space. Okay? Now, is our solar system empty? It's mostly empty, right? Does that mean that the masses that are in our solar system are unimportant or uninteresting? Absolutely not. Okay. Then I come in closer and I don't see Mars because Mars is over here in its orbit. And then luckily, I'm going to wave at planet Earth. I'm going to wave at everybody, all of us on it. I'm coming closer. And what do you imagine happens as we get in close to the sun? Do you think that if we're traveling at a constant velocity, this just stays constant? Probably, and I hope, that you imagine that as you get closer to the sun, it starts pulling you in and you start moving faster and faster and faster, and then bam, crash into the sun and burn up. Yeah, this is such a happy ending. Why is that? Well, because you already have an idea about gravity, right? So I want you to back up and notice some of these things that we've talked about. First of all, mostly empty, right? Even though it's mostly empty, when we say empty, do we mean volume or mass? The sun is very massive, right? The sun is massive and has a lot of gravity. Out of all the planets, which are not drawn to scale, Jupiter is massive and has a lot of gravity. If this were drawn to scale, I'd have a bigger gap around Jupiter because Jupiter has so much mass. It has a lot of moons. Probably it pulled objects in because it has so much mass, it has so much gravity. It pulled objects in to become its moons. And that's why there's a big gap between Jupiter and the next planet. Our inner rocky planets, Mercury, Venus, Earth, and Mars, and then a big gap, and then our gas giants, right? 2 gas giants. Saturn also, big gap between Mars and Jupiter, Jupiter and Saturn. Now this is in the real solar system. What am I saying? Mass and gravity are here. There's real masses here, there's real forces here, and yet the space is mostly empty. So notice where the volume is empty. Notice that there is mass, but in very specific places. Okay? Now, the Jupiter part of this analogy is going to fall apart because it's not a perfect model. But the sun being very massive, that's an important idea. Hold on to that. Okay, so we flew in. We did not encounter very many planets as we flew in, and then as we fly into the sun, we get pulled into the sun because it is so massive. Let's get a little more into the forces involved, okay? I'm going to put a temporary pretend planet here, okay? Now, what are the forces acting on this planet and all the planets? We talked about the gravity, right? There is a gravity vector pulling it in towards the sun. It is a force that is directly between whatever object you're looking at and the sun, straight line. Well, so if I just put a rock out here, it would eventually just fly directly into the sun. So why don't the planets just fly directly into the sun and they'll crash into the sun? Thankfully, they do not. Oh, because they're in motion, right? They're in motion. And so here's our planet, happily, and we have a velocity sending us in this direction, and the gravity of the sun pulling us in that direction. And actually imagine the, let's see, you go off, and then the gravity of the sun pulls you back in. Your velocity sends you off, and then the gravity of the sun pulls you back in. This doesn't actually happen in lots of little steps, but this is a good example of how these two forces balance out to make an orbit. Our velocity doesn't want to go in a curve. Velocities like to go in straight lines. So our velocity and the gravity of the sun pulling us back in. So we have this beautiful balance that ends up in this orbit. Okay, so if I dropped a smiley planet rock out here and he wasn't in motion, he'd fly into the sun. If I throw smiley face rocky planet out here and he's moving really, really fast, really, really big velocity vector, he's just going to fly off. Whoops. Fly off out of the solar system. okay? It's got to be just the right balance. And our 8 planets and lots of other objects and asteroids and stuff have just the right balance between the force pulling them in towards the sun, which is gravity, and the force sending them around, which is their velocity. Would it be a good thing if our planets got real close to each other? Probably not, right? They'd crash into each other. We don't want that. Okay, now, how is this like the atom? Okay, we're going to give you the answers here. We have 3 subatomic particles that we're going to do a bunch of work on. These outer planets are like our negative electrons, and the nucleus has positive protons and neutral neutrons in them. Okay? So our planets out here, I gotta make them much smaller. They can still be colorful. Okay? And again, this is not to scale. Our little electrons with negative charge. It really wouldn't be 1 electron per orbit, but we'll get into that. Our sun is the nucleus, which has protons and neutrons in it. Now, I'm going to do a little cheat here. I'm going to draw a nucleus. 1, 2, 3, 4, 5, 6, 7, 8. And I'm just going to write in that space what is in there, instead of drawing all the tiny little particles. That gets tedious. So in this nucleus is 8 protons, okay? Lowercase p for proton with a floating positive sign. Every time you think of protons, you're positive, you're for something, right? Protons. I want you to imagine it that way because the positive charge is so essential to the behavior of this particle. Now I have a little choice here. I'm going to throw in 8 neutrons in here as well. It could be a little more. It could be a little less. But I'm just going to say 8 neutrons, lowercase n. Now neutrons are neutral. So should I have a plus sign floating here? Should I have a minus sign floating here? Nope. A little 0. 8 neutrons are neutral. Now, what is the stand-in for the 2 forces? How are the 2 forces the same as what we just drew for the solar system? And how are they different? If you have a chance, I want you to pause the video. I want you to think about this. I want you to jot down some ideas. This picture of the atom, how is it similar and how is it different from the solar system picture that you looked at before? And especially, what's with these forces? Okay, when this was the solar system, this was the force of gravity, and this was velocity, because the planets are in motion. Okay? Okay, see if you can pause this. Welcome back. Okay, this one's the same, right? This force right here is exactly the same. The electrons are in motion. They have a velocity. If they were traveling too fast, they would fly off the atom. If they were traveling too slow, they would crash into the nucleus. That doesn't happen. Doesn't nucleus just mean center, right? Nucleus means it could physically be the center, or it could be a metaphor that's like the center of control, right? So the nucleus of a cell has the DNA in it. It's sort of in the center of the cell. It could be a little off to the side, but it is the center of control, right? The DNA is not great at biology, making the proteins that run all the processes, let's say. It's in charge, right? If you think of any nucleus of, let's say, the high school, you might think that the main office is the nucleus of the high school, right? Because it's the center of control. In this case, we mean both the center of control and the actual center, the physical center. So it's very convenient. The nucleus is in the center and it is in control. How is it in control? What do you think? Did you come up with any ideas about what this force is? Now, I'm hoping this is obvious if I really emphasize the positive charge of the protons and the negative charge of the electrons. This is basically a magnet. You could call this an electrostatic attraction. It's just how magnets work. Opposites attract. So this force right here, instead of being gravity, is an electrostatic force of attraction between oppositely charged particles. Now, I'm sure that's exactly what you wrote. Electrostatic force of attraction between oppositely charged particles. Maybe you wrote something about charges, opposites attract. It's like two magnets, you put the north and south ends together, and the opposite ends will attract. Now, what happens if you take two magnets and try to put the two south ends together? They will push, they'll physically push back. Now, you're probably strong enough that you could force them together. If it were a very strong magnet, you wouldn't be strong enough. But it is something that is different about the atom versus the planetary model. These electrons that all have negative charge, they're actually going to repel each other. Now, planets going around the sun don't repel each other because they have the opposite, the same charges. So this is a difference between a real atom and the planetary model. Like charges repel, opposites attract. This picture really gets us a picture of the atom. If we were going to fly in, we would notice some other similarities. If I fly into the atom from here, maybe I see an electron, but mostly I don't. Oh, there's another electron. There's 8 electrons here, and if I fly in over here, I'm only going to encounter a few of them. It's going to be mostly empty space. And then if my car is acting like an electron, if it were negatively charged, okay, it would be pulled into the center. It would be pulled in like the sun pulling it in because of these opposite charges. Okay, so an atom is mostly empty space, just like the solar system. Does that mean that it doesn't have mass? Bam, that's where all the mass is. All the mass is in the nucleus. This is another slight difference. This is like the sun, but the planets, our little electrons, are so light compared to this that we say they weigh nothing, okay? And we say that all the mass is in the center. And actually, it's not that far off from the solar system because the masses of the planets are not nothing, but they're almost nothing compared to the mass of the sun. That is actually the truth here. The masses of these electrons are not nothing, but they're almost nothing compared to the mass of the protons and neutrons. Nice thing about chemistry, we do a lot of close enough things. That's close enough to 0. So the electrons weigh essentially nothing. The protons and neutrons weigh about the same as each other. We basically round them, again, close enough to be about the same. And this is all of matter. Now, think a little bit about this emptiness. It's a little spooky. All the objects you know feel very, very, very solid to you. The solid objects, at least. And yet, they are mostly empty space. Mostly empty space. Mostly empty space. Why do they feel so solid? Well, the negative electrons on the outside of every object are going to try to repel the negative electrons on the outside of any approaching object. And even though they're mostly empty space by volume, that doesn't mean there isn't important mass in there. There's still mass. Okay, hopefully this has given you a bit of an as accurate as we can get, picture of the atom. This, by the way, is way too big. Okay, the nucleus would actually be tiny, 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 1/10,000th. Besides understanding what it looks like, we're going to figure out how we got here historically, and we're also going to master all of the numbers and symbols that tell us exactly what atom we have. For instance, this happens to be oxygen. It happens to be oxygen because, remember, the nucleus is the center of control. 8 protons tells me it's oxygen. We're going to get more into what that means. Okay. See you soon.